All right, looking at the calendar here. It's Tuesday. Remember that we really didn't do this yesterday because we just played a little bit of catch up. So we'll do 2 lessons today. Neither is that difficult. And you could argue they go together because they accomplish the same thing just in different ways. We also don't have to have any homework to go over, so we can jump right in and start doing notes on it. Homework will be due on Friday. Notes included there. And the homework will be that's due, Friday, will be the. I'm going to back off on what's due, or at least what's due on Friday. 103, 103, and 114. So the assignment from Friday and then the 2 assignments from today will be the only thing that's due on Friday. Again, I don't like picking up something the day after I assign it because I want you to have time to ask questions, to review it, to understand it, rather than just copy straight from CalcChat and turn it in, because that doesn't really help anything. So what you already have done, hopefully done, because we did some of it yesterday, and then the 2 assignments today, that's what will be due on Friday. And then that block day assignment will be due the test day the next week. So 103, 103, and 114. So 103 from Friday, 103 from today, and 114 from today. So 3 things due. And again, you'll have the 2 assignments today. You'll have several days to do because it's not due till Friday. Again, as best I can, I don't like taking up stuff the next day. You should do it that night, but then I want you to have an extra day to process it, think about it, ask questions on it. One more thing before we get to the notes, and that is, it's blocked, so I don't know how helpful this is right now. It's blocked on the school Wi-Fi, but I found the PDF of the textbook. So I tried to take a picture and post the PDF of that day's assignment. It's already in for today. But if you ever want more examples, or I don't post the link, or don't post a picture, then here's our Schoology page. We go to class information. CalcChat, again, great resource. Don't forget there's a tutor attached to CalcChat, so it's not just answers and work. It's like there's somebody live on the other end that can explain as best they can via chatting. Calendar, that's good to know. But I found the PDF of our textbook. And so if you ever need something, examples, explanations, or just the homework assignment, you could click that. Now, again, it's blocked right now when you're on school Wi-Fi, but if you're at home and you click it, it should be available. I'm not real sure the copyright of, because it's not the publisher that posted that, it's somebody else. So I'm not sure the legitimacy of that, but I'm not hosting it. I'm just telling you it's out there. Again, if you try to find it at school, I think it's going to block it. But if you're at home, you can pull it up. Yeah. Oh, it took too long to respond. That doesn't mean blocked. Try one more time. Anyway, it's a large file because it's a PDF of the entire 500-page book, but it's there. Maybe. Maybe not. Maybe it's just too big. Maybe it's blocked. I don't know. Anyway, when I'm at home, it works, and sometimes that's where I find what I post because I don't have a textbook at home. So I'll go to that website, screenshot what I need, and post it for you guys. So I just figured I'd give you the link. It's not coming up, but oh well, it looks just like the textbook. All right, let's talk about the 2 things for today. Again, a little bit longer lesson today because we doubled up so that we'd have time to kind of catch up from yesterday, make sure we were all on board with the definition of a derivative. I really like that, this to load, but I guess it's not going to. check back later. So alternative definition. So we try to separate the two definitions because they're really similar, which is, I guess, good because they kind of work the same way, but they're so similar that people get them confused. So we put them on different days, even though they're really in the same section in the book, 2.1, 2.1. But we try to separate them so you don't get them confused. And then the power rule is basically the shortcut to the definition. So there's one more long way around, and then we'll learn the shortcut way around. All right, alternative definition or alternative form. The big difference in what you find, so not how you find it, but what you find, is you find the derivative at one particular point. So you find f prime at c, so at some point, like 2 or 3, and you figure out what that slope is. For the original definition, you find f prime of x. So those look similar. They both tell you derivatives, but c is at a particular point, at one specific point, with an x in there. That's at any value of x. So they both tell you the derivative. The alternative form tells you, like, gives you an answer. You'll get the answer of 3 or 5 or 12 or -2, whatever. The general definition, the original one, not the alternative one, gives you usually an equation that has x in it, or an expression with x in it, and then you plug in whatever you want to plug in to find it. So the alternative form is a little easier, but it only tells you at one specific point. The original definition is a little bit longer, but it's more generic. This will make more sense when we do some of these. Let's look at a picture, because I think a picture can help lead us to the alternative definition. So some piece of a parabola maybe, who knows? It doesn't really matter what the picture looks like. There's C, so that's the specific value. We're looking for the slope at that line. All right, so there's our tangent line. But finding the slope at one point is, without a derivative, is kind of impossible, because you need 2 points to use a slope formula. So we're gonna sort of approximate that slope with a different line, but a line that has 2 points on it. And that's called a secant line. So a secant line is not really that helpful. Like, if I want to know the slope at C, secant line doesn't tell me that. I want to know the slope of the tangent line. But we're going to use the secant line to get to the tangent line. So let's write the slope of a secant line. And that's just, we need another point out here. Let's call that point x. So there's x and f of x, because we've got to have 2 points if we want to write an equation. So f of x minus f of c all over x minus c. again, that's a true statement, but if I want to know the slope at the point, the secant line isn't exactly it. It might be a decent approximation of it. What could I do with x to make my secant line be a better approximation of the tangent line? Like, how could I make my secant line closer to my tangent line? Where could I move x? Closer to C. If I moved x closer to C, well, then my secant line would start to get closer to the tangent line, right? And if I put it right next to it, then it'd be really close. And if it was super close, then we could say, that's pretty much it. In fact, what we want to do is take a limit. The slope of the tangent line is the limit as x approaches C of the secant line slope. F of x minus f of c all over x minus c. And if we have the slope of a tangent line, that's what a derivative is. So what we just wrote was the derivative at c. So there is our alternative form. So the two big things you have to memorize for the next test are the definition of a derivative and the alternative form of the definition of a derivative. Now let's kind of back up a little bit and put a couple of different names on these things. These two names are important all year long. In fact, we've started teaching this in pre-cal. I don't think we use this term in pre-cal with you guys. The average rate of change. Average rate of change. Well, rate of change, that's the slope. Like up 1 over 1, rise over run, y over x. The average rate of change means instead of exactly at one point, we'll look at two different points. So this is kind of an algebra slope problem. And really it's the slope of the secant line. So average rate of change is the algebra rate of change. Let's do a quick example. So this is an easy thing to do. It's just algebra 1 slope, which we've done a couple times in here. It's just you have to understand what they're asking for. So let's find average rate of change. On 1, 3. And instead of an equation, they give us a table. 1, 4, 2, 6, 3, 9, 4, 16. Find the average rate of change. Average rate of change means use algebra. Rate of change means slope. So this would just be f of 3 minus f of 1 over 3 minus 1. Just good old algebra 1 stuff. So this little section is, you know how to do it, it's just kind of a new term, average rate of change. So y of 3 is 9, y of 1, or f of 1 is 4, 3 minus 1. And then I guess just to emphasize the safe stop nature of questions in here, I'm going to leave it like that. I realize that probably bugs some of you to leave it like that, but that's part of why I'm going to leave it like that. Force you to be a little uncomfortable and lets you, again, emphasize that safe stops are okay. It's not cheating. You're not working the system. I mean, you are working the system, but legally, it's an okay answer to have. Roman numeral 2, instantaneous rate of change. Well, again, rate of change means slope, but an instantaneous slope, that would mean like slope at one point. So that's not algebra. You can't do that in algebra 1. But you can do it in calculus. And a calculus slope is a derivative. So that first word of rate of change is super important. Average goes with algebra. So the A's go together. Instantaneous, that one's easier to remember because you can't do an instantaneous rate of change in algebra. Like, remember very first day when I asked you to find the slope at A or B or C, you're like, how do I find the slope at a point? That doesn't make sense. And you're right, in algebra, it doesn't make sense. You have to have calculus to find an instantaneous rate of change. To tie it to what we did earlier, that would be the slope of a tangent line. Again, the only way to get the slope of a tangent line is with calculus, with limits. Alright, so let's find the slope of a tangent line. By the way, there's like 5 different ways to ask you to find a derivative. And so part of this unit is learning how to take a derivative. That's like one thing to do, but also learning the 5 different ways we ask the question, including instantaneous rate of change, derivative, slope of a tangent line. That all kind of means the same stuff. Find the slope of a tangent line to y equals 3x squared plus 2x minus 1 at x equals 2 using the alternative form. We have to say using the alternative form because you could do this problem using the original definition, and in about 20 minutes you'll be able to do this problem using the shortcut method. And so you're going to have 3 different ways to work this problem. So if we want you to use a certain method, we'll have to tell you which method to use. And then on the test day, sometimes we'll tell you which method to use. Other times we won't specify, and everyone will pick the shortcut method, but I guess you could pick whatever method you like. So slope of a tangent line, that's limit as x approaches c, f of x minus f of c over x minus c. That's the definition, the alternative form of the definition. To me, I find that one easy to remember because it's a slope formula with a limit on there to force the secant line to become the tangent line. So to me, that one's easier to memorize because it's not so much memorizing as it is understanding. That's the slope of a secant line if I cover up the limit thing. But I don't really want a secant line. I want x to be really close to c and turn it into a tangent line. All right, for this problem, c is 2. So I want the limit as x approaches 2 of f of x minus f of 2 over x minus 2. So f of x I know, x and 2 I know. I need to find f of 2. So take my function, plug in 2. Let's see, 2 squared is 4, times 3 is 12, plus 4 minus 1. Sometimes people ask about safe stops right here, and if that was your final answer, you could safe stop that, but we need to use f of 2 in this equation over here. So I don't really want to leave it as 12 plus 4 minus 1. Like, it's not wrong, it just won't be helpful later on. So 15. Limit as x approaches 2. Alright, f of x is, as x approaches 2, 3x squared plus 2x minus 1 minus 15, because that's f of c, or f of 2, all over x minus 2. So 3x squared plus 2x minus 16 all over x minus 2. If I plug in 2 like I'm supposed to do, start with, I'm going to get 0 over 0. So I need to factor this and hope that it works. Now, there's good news for these factoring problems, and that is, what do we hope happens after I factor this? What's the point of factoring this? Yeah, I saw somebody do the swipe out sign. Like, we hope that x minus 2 cancels. These problems sort of, it's not magic, there's a lot of math behind it, but that x minus 2 is going to cancel. So if I know that's going to happen, then factoring becomes a lot easier because I'm almost positive that x minus 2 is going to be one of the factors. So even though there's a 3 out front, which is usually harder factoring, you're basically given one of the factors. So start with x minus 2, and then grab a pencil and play around to see what else needs to be there to make it work. Well, this would have to be 8. That's not really a pencil thing. That's the only thing it could be. To get to negative 16, this is going to have to be a positive 8. Well, let's double check. So that would be 8x minus 6x is 2x. So it is factoring, but we basically spot you one of the factors every time. X minus 2's will cancel. Whoops, I got lazy and left off the limit as x approaches 2. So 3 times 2 plus 8. I could leave that as my answer, but I want to say something about that. So that's 14. But what we just found is the slope of this line at x equals 2 is 14. Slope of the tangent line at x equals 2 is 14. Now you don't have to write all of that, but I just wanted to review to make sure you understood what we just found. Right? Sometimes we get lost in the process and we sort of lose, forest and trees issue here. Like the trees, the details is taking the limit, factoring, canceling, plugging in. That's the tree issue. The forest issue is, wait a minute, what did I do all this for? Well, I found the slope of the tangent line at x equals 2. Let's do, let's not do one more of those. Let's skip to the new stuff. So, slope of a tangent line using the alternative form. There's our formula. Again, I don't think it's a hard formula to remember because it's the slope formula. Stick a limit on there to change it from a secant line to a tangent line. All right, now for the good stuff. This is one of those times where you're like, well, why didn't you just teach that first? Why do we got to go through all the long stuff? And now you're just going to tell me the shortcut that takes no time at all. I don't know. There's really good answer to that, other than we want you to understand what's going on, not just memorize rules. So 2.1 is about understanding what's going on. Technical definitions, limits. 2.2 is, all right, let's just talk about the shortcuts and get there quickly. Derivative of a constant. The derivative of a constant. I guess that'll be Roman numeral 1. It's going to be a quick one. So let's say we have y equals 3. 1, 2, 3. So there's my line, y equals 3. Not very exciting. What does the derivative tell you about a graph? You should have these two words like locked together. When you hear one, you should think the other. Slope. Derivative and slope need to be locked together in your brain for the rest of the year. They're not exactly interchangeable, but they're pretty darn close. So the derivative is the slope of a tangent line. Well, what's the slope of that horizontal line? 0. Slope is 0. So that means the derivative is 0. So the derivative of a constant is 0. Now you can memorize that, or you can think, well, a constant is not changing, so the rate of change, there is no rate of change, is 0. So you can think about the picture, you can just memorize it. I'd rather you have it understood rather than just memorized. Next, a little bit of a new symbol there, ddx. What that means is take the derivative of. The first calculus teacher long ago got tired of writing take the derivative of in his instructions, so he invented this nomenclature to say take the derivative of. I don't know if that's exactly how that story goes, but basically that's it. Like, instead of saying take the derivative of 100 times, we can just say ddx of c, take the derivative of a constant, and you get 0. So we'll use that symbol often. All right, the power rule. You're going to like the power rule. And you're going to not like me for waiting a couple days to show you the power rule. So ddx, take the derivative of x to the n. So here comes the rule. X to the n would mean x to any power. X to the second, x to the fifth, x to the 100th, x to negative numbers, x to fractions. So n can be any real number, n can be. Here's the rule. So the derivative of x to the n, now, I'm trying to hype this up a little bit. Before the shortcut, we would have to do, don't write this down, but here's a memory thing. Got to know. We'd have to do that, right? That's an h down there. So we'd have to plug in x plus h to the n, multiply it all out, do all the algebra. Not anymore. You bring the n down front as a coefficient, and you decrease the power by 1. And that's your derivative. So I'll write that symbol out in words here. Bring exponent to front as the coefficient, and decrease the power by 1. So some examples. You'll see how fast these go relative to doing the definition way. X cubed minus 4x plus 527. And we want to find the derivative of that thing. So x cubed, the derivative of x cubed, and by the way, with derivatives, because they're limits, we can add them, we can take the derivative of the pieces and just add them back together. So we'll go piece by piece here. So for x cubed, I take the 3 and bring it down front, and then decrease the power by 1. So 3x squared. That's way easier than the limit process. How about the next piece? What's the exponent on 4x? 1. So the 4 kind of just goes along for the ride. The 1 comes down. Decrease the power by 1. If we decrease 1 by 1, we get 0. We'll clean that up in a minute. And how about the derivative of 527? Ignore the rest of that stuff. It's 0. Because 527 is a constant. If you ignore the rest of this stuff, it's a big constant, but it's just a constant. So the rate of change of a constant is 0. I don't really recommend this, but you could write that as x to the 0. Right? Because x to the 0 is 1. You bring the 0 down front 0 times, and it just wipes out the rest of it. It doesn't matter. So it still kind of follows the power rule. Right, so 3x squared. X to the 0 is 1. So minus 4. By the way, let's zoom back in on that 4x. If we had just the graph of 4x, what shape would that be, first of all? What would the shape of 4x be? Okay, yeah, a line. Like, what would the slope of that line be? 4. What is another word for slope in this class? Derivative. So the derivative of 4x is 4 because the slope of a line, negative 4. Slope of a line negative 4x is negative 4. So it fits the power rule, but it also just fits the slope of a line rule. All right, let's get a little more complicated here. That's the answer. That's it. So once you get the hang of the power rule, this goes really fast. Way faster than the definition.
So how do you know what's a constant?
Good question. How do you know this is a constant? It didn't have any x's on it at all.
Okay.
So just a number. The derivative of any number is going to be 0.
But then something to like the 0 power is 0 or 1?
Something to the 0 power is 1. So if I want to use the product rule, like I really want, or the power rule, then I could write x to the 0 because that doesn't change anything. X to the 0 is 1. And then if I use the power rule, the 0 comes down front, and then it kind of doesn't matter what happens after that because you got 0 times. Doesn't matter. So again, this is like forcing the power rule. I'd rather you just know the derivative of a constant is 0. But still fits the power rule. If you really want to, say, I don't want to memorize the constant rule, I only want to memorize the power rule. You can do that. All right, well, that was kind of easy. So we need to come up with some wrinkles to make this a little bit harder. Right? You're like, man, the homework would go way too quick if that was it for the power rule. And nobody wants that. Like, we want to challenge ourselves a little bit here. No one. Like, no, we're good. We can stop here. 5 over 2x cubed. I want to use the power rule, but there's not a power rule for something in the denominator. Like I have to have x to the n, not x to the n in the denominator. So is there a way, my algebra expert friends, to rewrite this as x to some power where x is not in the denominator? Yeah, I could flip it. So leave the 5 halves alone. And when you say flip it, what do you mean? Like, what am I going to write here? 5 halves? X to the, what will the power be? -3, right? Because the negative is, like, this is a little backwards from what we usually do. Usually if we have a negative exponent, we put it in the denominator because we don't like negative exponents. Here we're taking one that's in the denominator and moving it up because now we can use the power rule. So power rule still applies now that we don't have it in the denominator. 5 halves just going along for the ride. -3 comes down front. Oh, and here's what gets people. This is so disappointing when this happens. Disappointing to me, disappointing to you when I hand your test back. We want to decrease the power by 1. So if I have x to the -3, I start at -3, and I decrease by 1, -4. Now everybody gets it when I slow you way down and talk you through it. You can probably guess what a common mistake is to put right there. -2. Like, yeah, 3 minus 2 is 1. Well, yes, but -3 minus 1 is -4. So, yes, the power rule goes quick, but please be careful when you got negative exponents or fractions. You're still just taking away 1, but slow yourself down a half a step so you don't make a dumb mistake. This is a perfectly acceptable free response answer because we're okay with negative exponents. We don't have to multiply stuff out. Like, nothing wrong with that answer. But on a multiple choice test, it's probably going to be cleaned up a little bit. -3 times 5 would be -15 over 2, and we'd probably put that x to the 4th back in the denominator. So again, those are equivalent answers, equally okay, but you better be able to get from the free response type answer to the multiple choice type answer, because on a multiple choice test, that's not going to be one of the answer choices. It's going to be cleaned up. So multiple choice, usually test your calculus and your algebra to make sure you can get to where you want to be. All right, the book asks questions in a little bit different way, so I want to ask a question the same way the book asks it, just so you understand what they're talking about when they do this. G of x equals cube root of x minus 1 over x squared. So the book is going to give you some steps to follow. It's going to say, first rewrite that. And when they say rewrite it, they just mean get it ready to use the power rule. Because I can't use the power rule with the roots. I can't use the power rule with the denominator. So it means, like, clean that up a little bit so that we can use the power rule. So what's the cube root of x written as a power? 1/3. And then we just did one like this, so that'd be x to the -2. So when the book says rewrite, like, the book's going to kind of make a table, and if we don't do this exercise, it's a little bit confusing as to what they're looking for. Differentiate. That's another word for take a derivative. So do a little prep work. That's the rewrite phase. Differentiate means take a derivative. So 1/3 x to the, oh, here we go again. Subtracting 1 has never been more difficult. 1/3 minus 1 is -2/3. Yeah, you still know how to do it. It's just when you get going fast, sometimes people panic. Minus -2 comes down, x to the -3. So that's an okay answer for a free response answer. But then the book says simplify. So that means clean it up, basically. Like, don't leave it like that. Let's clean this up a little bit. So a negative exponent goes to the bottom. Two negatives become positive. X to the third is going to the bottom for sure. What about that 2? Is that going to the bottom or staying in the top? Does the 2 have a negative exponent? That's the question. No, just the X does. So the 2 will stay in the top. So that's how we try to, not trick you, but get you a little bit on power rule, is with fractions, with negatives. So it's not hard, it's just be careful. Don't make a dumb mistake. All right, we're going to have to abbreviate a example. So we'll do 1.5 examples. X squared plus 3x minus 1 over x. Well, I can't do that yet because that's a quotient. We'll learn the quotient rule tomorrow. But I can clean it up, like I can divide everybody by x. X plus 3 minus 1 x to the negative 1. That's not a derivative, that's just cleanup work. Then I could find a derivative. So dot dot dot, meaning we don't have time to finish that problem. All right, now last example. Find the derivative of any points. F of x equals x squared times 1 minus x. Find the derivative. So that would be one part of this problem. And second part of this problem, any points x, y that have a horizontal tangent line. Horizontal tangent line. That shows up a lot. So show me with your arm what a horizontal tangent line would look like. Good. Everybody's doing this. What's the slope of the line? What's the slope of your arm right now? 0. So that's a fancy way of saying slope equals 0. But slope is the same thing as derivative. So really, it's a fancy way of asking, find where the slope is, find where the derivative is 0. All right, so f of x. I can't do this yet because I can't multiply derivatives, so I need to multiply first and then take a derivative. So distribute, that's not a derivative yet. Then take a derivative. 2x minus 3x squared. So there's step 1. And then I want to find where that is 0. So 0 equals 2x minus 3x squared. Let's see, factoring. Oh, this is not a hard factoring problem. What can I factor out of that? An x. That leaves 2 minus 3x. Set them both equal to 0. So x equals 0 is one of my points. And move things around a little bit here. X equals 2/3 is the other point. So there's two places that have a horizontal tangent line. X equals 0 and x equals 2/3. It asks for a point, so I need to find the y value. I don't have time to find the y value, but I would just plug it into the original, not to the derivative, but to the original, to get the y value point. So I'd have 2/3, comma, something, and 0, comma, something. All right, two more quick things that the book, I don't know why it does these yet, because we don't really want to talk about trig yet, but I'm going to give you two quick ones that you need for today's assignment. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. For now, you don't really have to have those memorized. You will need them soon enough. But for now, you can just kind of refer to them. Again, I wish the book would not throw those in yet, but oh well. All right, the assignment is a little bit different than what's on the calendar. 3 through 35, 45 to 49, 53 to 63, odd. Oh, and from the previous, so that's 2.2. The previous assignment is page 103, 65 to 79, odd. Now, the 2.2 looks like a lot of problems, but remember that's the power rule, so that's the shortcut. Those are the ones that go quickly. And again, that'll be due Friday. All right, so longer day today, but two kind of easy things. The homework's really not too bad because the concept's not difficult. All right, let me again encourage you to keep up. Don't push this stuff off, because then it snowballs and you can't understand what's going on. Like, keep up with it every day so that when we add a little bit tomorrow, you won't be further behind. You'll be on track.